Hi everyone, welcome to week 6 for the AI engineering book club. This week we are going to talk about two very important and commonly used techniques in AI engineering, RAG and agents. And today we have two speakers, Ray and Nanqing. So they are both graduate students at UC Berkeley. Then Ray will talk about RAG and Nanqing will talk about agents. Please go ahead, Ray, for your presentation.
All right. Thank you, everyone. Super excited here to talk about some RAGs and agent stuff. All right. I want to start from like fundamental aspects of how AI models work, especially when it comes to solving tasks efficiently. At its core, for an AI model to successfully complete a task, it requires two key ingredients. Firstly is like clear instructions on how to do the task and the necessary information to work with. So thinking of it like asking a person for help, they need to know what you want them to do and have the information required to do it correctly. Just as a person might give a wrong answer if it lacked the right information, AI models are more likely to make mistakes and even hallucinate, generate incorrect information when they are missing crucial context. This highlights the critical role of providing models with the knowledge they need. Now, it's important to distinguish between two types of input a model receives. One is the instructions on how to perform a task. They are generally consistent across different requests or queries. And then the other is the specific information for the context needed will vary greatly depending on each individual query. Given the importance of having the right information for each specific query, this chapter focuses on how we can effectively construct relevant context for each unique task we ask our AI models to perform. So there are basically two leading ways that we construct this kind of context. First, we have our retrieval augmented generation, or RAG. This pattern focuses on retrieving relevant information from external data sources to provide the model with the necessary context for a specific query. Think of this as giving the AI a targeted set of documents to read before answering. The second dominant pattern is the agentic pattern. This goes beyond simple retrieval by allowing the model to use external tools, such as web searching engines and news APIs, to proactively gather information. Importantly, agentic systems can also interact with the world, enabling automation. And next slide, let's talk about the RAG. So the definition of RAG is a technique that improves a model's output by retrieving relevant information from external memory sources. These sources can include internal databases, past user conversations, or even the internet. Essentially, we are giving the model access to a targeted knowledge base to inform its generation. So a little bit of history here. So the underlying retrieval then generated pattern was first introduced in a 2017 paper that explored using Wikipedia to answer open domain questions. And then the term retrieval augmented generation itself was coined in a 2020 paper. This paper specifically proposed RAG as a solution for knowledge-intensive tasks where it's impossible to feed all the necessary information directly into the model due to context limitations. A key finding was that by providing access to relevant information, RAG helps the model generate more detailed responses while also reducing the occurrence of hallucinations or inaccurate information. We've defined RAG so far, so now let's understand its purpose and why it remains crucial. RAG constructs context that is specific to each individual query, unlike a one-size-fits-all approach. This also helps in managing user data by ensuring user-specific information is only included when relevant. Think of context construction in RAG as similar to feature engineering in traditional machine learning. providing the model with the necessary information to process and input effectively. Initially, RAG emerged as a key technique to overcome the limitation of models' context windows. But even now, models' context windows have improved, but RAG is still likely to remain vital because there will always be applications requiring more context than any model can handle. Models with long context don't always use that context efficiently, potentially causing an irrelevant information, potentially focusing on irrelevant information. And also longer context leads to increased costs and latency. RAG focused the model on only the most relevant information, reducing input tokens and potentially improving performance. Interestingly, model providers might even integrate retrieval-like mechanisms into their own architecture. And lastly, guidance is starting to appear on when it's more appropriate to use RAG versus simply using long context windows. So now I'm going to introduce the architecture of RAG system. At its core, a RAG system has two main components, a retriever and a generator. The retriever is responsible for retrieving relevant information from external memory sources in response to a query. The generator then uses this retrieved information along with the original query to generate a response. Historically, in the original RAG implementation, the retriever and the generated model were trained together. However, in contemporary RAG systems, it's more common to use a pre-trained off-the-shelf retrievers and generated models. It is important to note that fine-tuning the entire RAG system, including both the retriever and the generator, could lead to a significant improvement in performance. The first key component of a RAG system we'll discuss is the retriever. Its primary role is to fetch the relevant information needed by the generator. The retriever has two main functions. Indexing. This involves processing the external data so that it can be quickly and efficiently retrieved later. The specific way data is indexed depends on how you intend to query it. The second function is querying. This is the process of sending a query to the indexed data to find and retrieve the most relevant pieces of information. A challenge arises because naively retrieving entire documentation in response to a query could result in an overly long context for the generation model. To address this, documents are often split into more manageable units called chunks. Once relevant chunks are retrieved, minor processing might be necessary to combine these chunks with the original user prompt before feeding them to the generator. All right, let's jump into how we can actually pull relevant information for our RAG systems. Now, the concept of retrieval isn't novel. In fact, it's a century-old field forming the backbones of things you're all very familiar with, like search engines. So the fundamental principles here are well established. The good news is that many of the traditional retrieval algorithms that have been developed over the years can be directly applied to RAG. This isn't about reinventing the wheel. In this section, we'll be covering the broad strokes of these algorithms. Given the depth of information retrieval as a field, we won't be able to cover every nuance here. However, for those who want to go deeper, the book's GitHub repository contains more in-depth resources on information retrieval. And then just a quick note on terminology. Within this chapter, the authors have been using retrieval and search somewhat interchangeably. Although typically retrieval might be thought of as operating within a single database or system, while search spans across multiple systems. At its core, retrieval, the primary function of any retrieval algorithm is to rank documents based on their relevance to a given query. This ranking is what allows us to surface the most permanent information to feed into our language model. Finally, it's important to understand that different retrieval algorithms vary in how they actually compute these relevant scores. So we'll be exploring some of these key differences next. So the first key retrieval method is called term-based retrieval. So they are essentially finding relevant documents using keywords. So there are some problems to this. The first one being many documents might contain the same term, exceeding the context limits. And second, prompts contain many terms with verifying importance, so it can make the model confused. So there is when we introduced a few different types of ways to evaluate, to approach this problem. The first one being term frequency, TF. That is the number of times a term appears in a document. The higher the frequency, the more relevance assumed. The second method is called inverse document frequency, IDF, measures the importance of a term. So inversely proportional to the number of document it appears in. So higher IDF means more important. And then we also have metrics like TF-IDF. So it combines TF and IDF to score documents relevant to a query. So we have some common term-based retrieval solutions out there. This includes Elasticsearch, Okapi, BM25. And then we can talk about embedding-based retrievals, where it's apparently more popular right now in all the RAG solutions. So in embedding-based retrievals, we rank documents based on semantic meaning alignment with the query. So this is called semantic retrieval. We aim to return documents relevant to the intent, unlike term-based retrieval, which focuses on lexical matching. So there are two steps of process. The first one is indexing, where we convert data chunks into embeddings using an embedding model stored in a vector database. The second step is querying. We convert the query into an embedding using the same model, and then we fetch the data chunks whose embeddings are closest to the query embedding using a retriever. So real-world system here might include re-rankers and caches. So this method relies heavily on the quality of the embedding models. So there's also another field where we're seeing a lot of competition happening. And then I want to talk about a very important part of the embedding-based retrieval, vector databases. So vector database is a kind of database that stores vectors and performs vector search, that is finding the close vectors to a query embedding. We efficiently using indexing. Vector search is common in various applications beyond generative AI. So there are many different kinds of vector search algorithms, but they are typically framed as nearest neighbor search problem. So we have our native solution, that is KN. We compute similarity between the query and all vectors ranks, and then returns top K. So this method is very precise, but pretty slow for large data sets. And then we introduce the approximate nearest neighbor algorithms. So this is used for large data sets to improve speed, trading some accuracy. Popular libraries here includes a list of library. And in the book, the author also offers a brief overview of the algorithms. There are many algorithms out here. As you can notice, there are many more and more traditional databases extending to support vector storage and search. So this is like a whole architecture with the embedding models, vector DB, retriever, and generative model included. So for the external memory, we'll get into a splitter, feed it into embedding models, and store it in the vector DB. And then when users submit the query will also get embedded using the embedding model. And then the retriever is going to compare the query embedding with the vector DB to fetch the context relevant to our query to the generative model. And then the generative model could have enough context to craft a very relevant response. So here, I want to summarize the key takeaways when it comes to comparing retrieval algorithms and evaluating their quality. Now we've looked at the term-based retrieval, I want to contrast it with embedding-based approaches and think about how we measure their effectiveness. One of the most immediate differences that you will notice is in querying speed. Term-based retrieval is generally much faster than embedding-based retrieval. This is because simple keyword matching and looking up terms in an inverted index are computationally less intensive than generating embeddings and performing nearest neighbor searches in a vector space. When it comes to performance, term-based retrieval can offer strong results right out of the box. Solutions like Elasticsearch and BM25 have a proven track record. However, it can be harder to significantly improve its performance beyond a certain point, and it's susceptible to term ambiguity, where the same word can have different meanings. Embedding-based retrieval, on the other hand, has the potential to outperform term-based methods, especially with careful fine-tuning of the embedding model and the retriever. It also allows for more natural language queries as it operates on the semantic meaning rather than just the keywords. Another critical factor is cost. Term-based retrieval is significantly cheaper than embedding-based retrieval. The latter incurs costs associated with generating embeddings, vector storage, and the vector search operations themselves. These costs can sometimes be a substantial part of an application's infrastructure expenses. It's also important to consider the trade-offs between indexing and querying. For both types of retrieval, a more detailed index can lead to more accurate retrieval, but this often comes at the cost of longer indexing times and increased memory usage. Now, how do we actually know if our retrieval is any good? There are several metrics for evaluating retrieval quality. The first one is context precision. This tells us what percentage of the retrieval documents are actually relevant to the query. Another metric is context recall. This measures what percentage of all the relevant documents in our database were actually retrieved. Calculating recall can be more challenging in production as it might require knowing all relevant documentations. To compute these metrics, you typically need an evaluation set consisting of test queries and a set of documents where each document has been annotated as either relevant or not relevant to each query. This annotation can be done by human or AI judges. If the ranking of the retrieved documents is important for your application, for example, you want the most relevant documents to appear first, you can use metrics like the NDCG, MAP, or MRR. Now we want to start comparing, evaluating the embeddings. For embedding-based retrieval, you also need to evaluate the quality of embeddings. This can be done in two ways. First is done this independently. Good embeddings should place semantic similar documents closer together in the vector space. Or you can do this task specifically. You can evaluate how well the embeddings perform on downstream tasks, such as retrieval, classification, or clustering using benchmarks like MTEB. Ultimately, the quality of the retriever should be assessed in the context of the entire RAG system. A good retriever is one that helps the system generate high quality and accurate answers. Regarding the semantic retrieval, while the added latency for generating query embeddings and performing vector search might seem significant, it can sometimes be minimal compared to the latency of the generated model itself, especially for long outputs. However, it's still a factor that it can impact user experience. Similarly, the costs associated with bad embeddings and vector databases need to be carefully considered. Finally, for those of you who are interested in diving deeper into the performance characteristics of different approximate nearest neighbor search algorithms used in vector databases, The ANN Benchmarks website provides a valuable resource for comparison. Additionally, BERT is an evaluation framework that supports retrieval systems across a range of standard benchmarks. Now, instead of only using term-based retrieval or embedding-based retrievals, you can actually combine retrieval algorithms known as hybrid search. This approach can enhance RAG by leveraging the strengths of different approaches, and this can be done in main two ways. The first is sequentially. That is, you use a fast but less precise retriever to get initial candidates, followed by a more accurate but potentially slower mechanism, like re-ranking with embeddings, to refine the results. Or you can do it in parallel. You run multiple retrieval algorithms simultaneously and then combine their rankings. A key technique for combining parallel ranking is called reciprocal ranking fusion. RRF assigns scores to the documents based on their rank in each retrieval list, with higher ranks receiving higher scores. The final score of our document is the sum of these scores across all retrievers. By strategically combining retrieval methods, either sequentially or in parallel with the techniques like RRF, you can achieve more accurate and robust retrieval for your RAG applications. Okay, we are getting into the end of RAG chapter. So we're talking about something very important, optimizing our RAG pipelines. We know that getting the right context to the model is crucial for accurate and insightful responses. Today, we'll focus on a few key strategies to fine-tune our retrieval process. First up, chunking strategy. Now, we break down our knowledge base significantly. How we break down our knowledge base significantly impacts what we can retrieve. Think of it like preparing data for a database. The schema matters. We are not just talking about arbitrary splits. While simple methods like fixed character, word, sentence, or paragraph length exist, consider more intelligent approaches. Recursive splitting can help maintain the integrity of related information by breaking down documents into progressively smaller units, only when necessary. Also, keep in mind that document-specific strategies can be highly effective. For code, maybe we split by functions or classes. For Q&A pairs, each pair forms a natural chunk. A key point here is overlap. Simply splitting can lead to loss of context at the boundaries. Imagine splitting "I left my wife a note" into two parts. Neither makes complete sense. Introducing a small overlap between chunks ensures that critical connecting information is preserved. Of course, chunk size must respect the context window limits of our foundation models and any embedding models we are using. Lastly, chunking by tokens, as defined by the generative model's tokenizer, can streamline downstream processing. However, be aware that switching models might require re-indexing. So there is a trade-off here. Smaller chunks can provide more granular information and allow more chunks within the context, but they risk losing broader context and increased computational overhead, especially for embedding-based retrieval. Experimentation is key to find the sweet spot for your specific data and use case. Next, let's talk about re-ranking. Our initial retrieval might give us a decent set of candidates, but we can often improve accuracy by applying a more sophisticated ranking mechanism. One effective approach is to use a two-stage process, a fast, less precise retriever to get a wider set of initial candidates, followed by a more computationally intensive but precise method, like KNN or embeddings, to re-rank those candidates. Think of this as a quick initial filter followed by a more thorough inspection. For time-sensitive data, re-ranking based on recency can be crucial. While the exact order is less critical than in traditional search, The presence of relevant document within the context is the main goal. Models tend to process information at the beginning and the end of the context more effectively. Moving on to query rewriting. User queries, especially in conversational settings, can be ambiguous. Rewriting these queries to be self-contained and reflect their true intent is vital for effective retrieval. For instance, a follow-up question like, how about Emily Doe, needs to be rewritten to, when was the last time Emily Doe bought something from us? This can be done using heuristic or more powerfully by leveraging other AI models with appropriate prompts. I also want to remind you that please be mindful that query writing can become complex when dealing with identity solution or the need for external knowledge. Our rewriting mechanism should ideally handle cases where information is missing rather than hallucinating. Lastly, let's discuss contextual retrieval. The idea here is to enrich our data chunks with additional context to make them easier to find. A simple method is to augment chunks with metadata like tags and keywords. For an e-commerce product, this could include its description or customer reviews. For code snippets, we might add function names or related concepts. We can also extract entities automatically from the chunks and add them as metadata. This allows for retrieval based on specific terms, even if the chunk itself is represented by an embedding. Another powerful technique is to augment each chunk with the questions it can answer. Anthropic has a particularly interesting approach. They use an AI model to generate a short, succinct context, around like 50 to 100 tokens, that explains the chunk's relationship to the original document. This generated context is then prepended to the chunk for indexing. So by strategically applying these retrieval optimization techniques, chunking effectively, re-ranking intelligently, rewriting queries thoughtfully, and enriching our context, we can significantly enhance the performance and reliability of our RAG applications. Remember, experimentation and evaluation are key to determine the best strategies for our specific needs. Lastly, I want to briefly talk about evaluating retrieval solutions. Key factors here include supported retrieval mechanism, embedding models, vector search algorithms, scalability, indexing time, query latency, and of course, pricing. So in the closing paragraph, the author also talks about the application of RAG beyond text. We'll have multi-module RAG, like argumentating with various modalities like image, videos, and audio if the generator is multi-module. Retrieval can be based on metadata or content. And then also RAG can deal with tabular data, different workflow involving like text to SQL conversion, SQL execution, a response generated to answer queries requiring information from data tables. May require an intermediate step to select relevant tables here. Yeah, so this is all my presentation about the RAG part of the chapter. All right, thank you. And then we're going to invite Nanqing to talk about AI agents.
All right. Thank you for Ray's introduction for the RAG, and now it's my turn to introduction the AI agent. Let me share my screen first. Okay. In this part, they are talking about the AI agent, and we will explore like what AI agent are and what they can do, and why they are considered a major steps in this AI development. So first question is about what is an AI agent. In the textbook, in this book, the AI agent they used a really straightforward definition. That's an AI agent is anything that can persuade its environment and act upon that environment. So in this mean, like, to understand an agent, we need to look at two main things. The one thing is environment it operates in, and the actions, the set of the actions it capable of taking. So like in the before we dive into the details, I think like in the AI agent in the recent application, including for example, the customer service chat box, they will answer questions and resolve the issues, or the autonomous robot in factories or homes, or the AI-powered assistant like ChatGPT, and with the web browser and the code execution or image generation capability, and also like the self-driving cars, they perceive road conditions and navigate accordingly. So the first one is about the environment. So first, the environment is defined by the agent use cases. So the textbook mentioned a lot of example. For example, in the game playing agent, if you're playing a chess game, so the chess board and the rule of the chess constitution is environment. And if that agent means the gathered information from the website, the internal itself is environment. And if we're thinking about the safe driving car, its environment includes like roads, traffic signals, and other vehicles, and even something like a coding assistant, like the SWE agent mentioned in the text in the book, operate within the environment of a computer's the file system and the terminal. Another part really important is the tools it access to. They mentioned like different tools, the three tools, the knowledge augmentation, and the capability extension, and acting on the environment, the writing actions. So for the first, for the knowledge augmentation tools, they will help agent to get information like RAG, and they also like the text retrievers, and the secure and SQL executors, and also broader the broader capabilities like web browsers to access up-to-date information. And the second is the capability extension, that especially mean like they can address the inherent limitation of AI models. For example, we all know ChatGPT is really bad at the math. So like rather than just solve this like using fine-tuning or other way to solve this limitation, they can just use the tool and to give an agent a calculator to make it good at math, and don't need to train anymore. And the third one is about the is different with the previous tools, that is right action. So they can allow the agent to act upon their environment. Like they can, for example, the email APIs, they can send emails or the data, or if they use the banking API, and that would be do the transfer like for these users. But these tools is really dangerous for normal people. They will think that's really horrible if the AI make decision for them, especially when that when that related to the money, like they can just directly to transfer money, and that's really horrible to a lot of people. So the tools, like in general, that's like the extensions of the agent's capability, allow them to interact with their environment in more specific, in more complicated ways. And when we're talking about this two part of AI agent, what make AI agent is really powerful, I think that is the AI agent's planner. Like AI agents planner, they can do a really amazing things. For example, this AI that acts as the brain that they can process this information and plans a lot of actions, and also to determine if the task is accomplished or not. So for this one, the book just used the really good example that is like the brain of the agent. So when giving a test, the agent will analyze the information, including the feedback from the environment, and plans a lot of actions to achieve the goal. In general, like for example, the agent will first reason about how to plan a chip or predict sales, and then we'll plan to use SQL and queries to get past the sales data, or using the web browsing to get the information. Then they will execute these queries and then reason about whether it had enough information. If not, they will continue to do the things to make sure they achieve the goal. A really important thing mentioned that is it's often best to separate the planning stages from the execution stages. This means like the agent will first come up with a plan, then only after this plan is checked to see it makes sense, and then carry out this plan. So it will really important to avoid the wasted resource. So it's not like once I have a plan, then just execute the plan and then evaluate, because that will waste a lot of resource and time to execute a plan that it doesn't work. The next part is about the failure. So when we're talking about these actions, we're talking about the planner. So in this when the agent do the planning, how to evaluate the planning's the performance is really important. Not only the planning, but also the execution. How to evaluate them is really important to make sure we can get a really good performance. So when we're talking about evaluation is about detecting the failures. So to evaluate an agent, like identify its failure modes and measure how often each of these failures modes happen are really, really important. And so the textbook mentioned three major failures: planning failures, tool failures, and the efficiency issues. So for the planning failures, it's mainly just about like they're trying to use a tool, but the tool it doesn't have access to, or just plan the the wrong kind of inputs to a tool, and also like they use the right tool, but it doesn't actually solve the problem, or just like can't meet the given requirement. The second is the tool failure, that is like the tool like they choose the correct tool, but the tool itself provides the incorrect information. And the last one is about the efficiency, like all the things is right, but it will cost too much time, and it will cost too much and also spend a lot of time to complete the task, which it's not efficient. So when we're talking about these things, like especially to be efficient, effective over time and across the multiple interactions, they really need the memory. So the book discussions 3 kind of the memory: the short-term memory, short-term memory, long-term memory, and internal knowledges. So in this, like the agent is mainly about the short-term memory and the long-term memory. So for example, if you have an AI assistant, the long-term memory could store your preference, allow it to personalize its actions with you. So for the context, the part is more like the immediately, the text-specific information. Like if you want to solve this problem, to do the planning, to execute the plan, you have to use that short-term memory. And if that is the long-term memory, that is, it would be help you to like to maintain the consistency and to make sure the long-term memory like can retain the information across the different tasks or seasons. I think like during the whole time about the AI agent, I think really important things is how to improve this AI agent performance. The first thing is about the reflection and error correction. So we're talking about the failures and talking about the failure modes and the evaluation. So it's mainly about that. Like we can choose, for example, when we let the AI agent to do a plan, then they do a plan with immediately to do the reflection, to do the error correction, and after that, we can get a better plan, and then we just like to execute the plan. Like every step, we just do the evaluation and to do the error correction to make sure like every step we will have a good performance. Then at the end, we can get a really good performance. So that's really important part to improve the agent performance. The second thing really important is about the tool selection. We already mentioned like the tool is really important for the AI agent. So how to choose the right tool is really important. The books mention in general, when you have a lot of tools, you can have a better capability, you can have a better performance. But it also means you have to like to select the right one to get the right tool from the lot of the tools you have for the agent and to execute the task. So they will have a lot of the different way. Also, I remember in the books they mention when they is about they will have a lot of the different strategy to do that. Like for example, the frequency. Like if you have like 20 tools, which tools you will use like frequently, and that means this tools is really useful for your task. And also different task will use different tool. So how to choose the right tool is really important for the AI agent performance. So in conclusion, like AI agent is considering like to be a significant steps towards the truly intelligent and AI, and by combining the ability to persuade their environment utilizing a range of tools and plan their actions, it's exactly to open the opportunities for automating complex tasks and assisting us in numerous ways. And also they already have a lot of the application in the tech company and in our daily life. But we have to see they still have a lot of challenge to overcome, like the ongoing research environment in this area promise a better future. Yeah, so that's all the things about the AI agent.
Thank you, Nanjing. Thank you, Ray. Any questions from the audience? Yeah, so I think both RAG and agents, as mentioned at the beginning, they are probably the most commonly used tools right now for the enterprise use cases. Especially for RAG, it's very useful for building chatbots or basically any applications that we need to have the references to the actual data. Because if we just use the general out-of-box foundation model, could be some risk of hallucination. And with the agent, it's also a step forward where we not only just getting the text information, but also to automate the task. So which is also be very helpful if we can increase the productivity by reducing those manual steps. And also there are a lot of tools coming out recently for the agent. I think for the agent, it's still a new field. Like there are a lot of tools coming out. And for the RAG, the tools are pretty mature. For example, they are just the vector databases usually already get the ranking and usually there's some big pairs or some selections people would tend to choose. But like Ray mentioned, it's still a lot of open questions regarding the evaluation and optimization, especially the latency space. For example, if you deploy a chatbot to the app, you don't, if it's very slow to respond, the user response experience will not be perfect. For example, when you shop on Amazon, essentially they have a Q&A system where you can type the question and they will use the customer reviews and product description as the database to retrieve the information from. I just tried earlier today, but it was just 3 to 5 seconds of waiting, which definitely I think there's a lot of room for the improvement. Because in the end, you want the users to feel just as smooth as possible instead of thinking whether this is RAG or agent in the backend. And yeah, so both of the presentations for this book club is tends to focus more on the theory and the concepts. And after the 10th week, we will also have some special sessions where you can present your side projects. So especially in RAG and agents, I think these are the areas and tools people tend to use for the side projects most often. So feel free to sign up there if you have anything to showcase. Yeah, any more questions? Rajat, do you have any questions?
Yeah, I have a question. So, how do people go about creating evaluation datasets for agentic systems?
Sure. So the question is the evaluation and creating the data set for the agent systems, right?
For the evaluation, they will let them to do the self evaluation, like for the agent, like they also they mentioned the failure modes. So it would be a good way to do the evaluation, like you to analyze like which general the failure you will have, then it would be easy to help you to improve your performance. Like in general, like you ask like 100 questions, you do 100 the task, and then you find like the most frequent failure that is the tool use and then you will find that there's something wrong about the tools. So you can just improve the tool in part. So this is like how they to do the evaluation and how they improve their performance.
Does that answer your question, Rajan?
So I guess it's mostly manual at the moment, right?
So I think there are some evaluation tools and like vendor softwares out there, but to start with, usually what I see is that people start with manual approaches. And by the way, in the production scale, you want more like real-time evaluation and monitoring, then using some open source or vendor software might be helpful. Yeah, also regarding the data preparation side, I think this is also a very important question and something that will be discussed more in week 8 chapter on data set engineering. So I think that chapter will also cover more details and best practices in terms of preparing data for either like fine-tuning or agent or RAG. I think in general, I think the most important thing to understand how the agent or RAG will use the data. So this way, you can use techniques such as mentioned in the condition, like chunking or better indexing, or put it another way, basically how you would do better data modeling and storage. So data modeling means how you design the schemas in the relational database. So this way, you don't want the agent to run a SQL query that will take a lot of time. But if the key information is stored in a very clear schema format, with just the essential information that the agent will need to do the planning and make actions, so this will be helpful. And the second part is the data storage, because there are different ways of storing the data. So one is relational versus unrelational, such as MongoDB. Like in Ray's presentation, the slide mentioned about lots of the traditional, well, basically not only the pure vector database, but also the existing database providers, they are also adding a lot of the embedding and the vectors capabilities. For example, MongoDB has been doing lots of new features in this field. So as well as Postgres, as well, they have an extension where you can store the vectors in the Postgres as well. And also for, say, BigQuery, which is traditionally for the OLAP analytics queries. But now you can also have the embedding there. So I think in this case, you can, depending on the use case, you can design the system like whether you want a separate vector base or not. Because if your data some are more relational, such as numerical data, some are textual information where you're storing the S3, like block storage, and some have the embeddings. So essentially, you want to also reduce the latency of fetching those data from. Yeah, so I think just similar to other software engineering best practices in terms of the data preparation, the key is to let the system find the data as efficiently as possible. For example, if you want this AI to say have a system to have a large file system, This is an example where you want to find some information from that file system. Imagine a world where all the files, the titles are not very descriptive, or just say the employee name. And then you can think of that they are not very ranked perfectly, because you need to do a search by the employee name separately. But in the other case, if for each file name we also have the employee ID, then this way we can rank and order these files more effectively. So if the agent just want to perform some action on that particular employee's files, they can more easily find the needed files and perform the actions. Yeah, so I think that's my 2 cents in terms of the data preparation part for your question, Rajan.
True, true.
I think also the key takeaway is that with RAG and agent, I think the entry barrier has been lower a lot in the past, not years, but just in the few months. We have tools such as LangChain, Llama Index, and recently OpenAI also has their toolbox for building the agents. So it's getting easier to build these systems, but also still also means more importance in terms of thinking carefully about evaluation and optimization, because it's not free. You still need to store the vectors, and even for agent, it's also not free. You need to deploy it somewhere and run the query and call the APIs. So evaluation and also optimization in terms of building the system. And also, I think finally on the evaluation side is just as mentioned in the previous 2 chapters. I think finally the business metric is still very important. For example, thinking about the coding agent. If we use the system metric, things will be latency and or like lines of the code, or the how many bugs in the code. But in the end, we want the agent, or basically the copilot, to generate the code that actually runs and passes our, say,
Save working hours.
Yeah, which is, I think, not really the case, right? Even though the agent can very quickly generate the code, but we might rather have it, think for a longer time, but generate a better solution. And also say if an agent is about booking the travel tickets, and the end result we want to see is that whether it actually books tickets with the lowest say prices as possible. And also, let's say for I think for another big use case is the customer support, which a lot of the companies have been deploying that. But even though if we use more like system metric, like the time to respond, which might not be the useful cases, because for customer support, we want to maximize the user, basically, happiness, not only resolving the user request, but also making sure the user feels they are being treated very fairly, and like we pay attention to their concerns. So that's why I think many chatbots, like when you end the session, they will ask you to provide some feedback, like whether you are satisfied with this support agent's request, whether this is a human or the AI agent, but we need to collect those feedback from the system. So that's another, I think, very important point, is that sometimes to do the evaluation, if we don't have enough metrics to measure what we define as the success criteria, we can also put into the system some of the feedback loop so that we can collect these evaluation number from the actual users. So this way we can further improve our system. So basically use the existing data with the feedback as a way to kind of reinforce learning and to improve the system further. Because this way we know, say, the generated answers, what are actually good and meaningful to the users and what's not. So this way we can let the AI better learn why some of the previous results are not that helpful. Yeah, so essentially the idea of the human in the loop. Any more questions? Rajat, Nanqing, or Ray?
So Liu, do you know of any examples where agentic systems have been deployed and like they have really added value?
Yeah, that's a
Business value.
That is, so for me, I have not seen any agents at work within the production system, but from what I know, lots of the companies put the agents in the tech strategy roadmap. Definitely something a lot of companies are trying to use more. So a good resources I would recommend is one is the OpenAI documentation on AI agents. They have use cases. Another is like recently some AI startup. One example is called Manus AI. So they have a page called use cases, which is really interesting. Let me put in the link. You can check out. Yeah, manus.im. So here they have a use case gallery, for example. So they also have a YouTube, the video embedded in their website. It's pretty cool. Like you can see what kind of task that their agents can perform. For example, here is like planning a travel, doing some research, data analysis, and also like find potential customers. So in general, from like online resources, I think there are several big use cases which I see have made some success. And the first one is data analysis. So it's about how can we democratize the data analysis to a larger audience. Before, you need to hire the dedicated data analyst who knows SQL very well to pull the data and prepare for the BI reports, say for the business functions. But now with the agents, the non-technical business users can also do these things very quickly instead of relying and waiting on the response from the data analyst. So that's, well, because this problem is much more well-defined, where for single query, etc., tell me the best-selling product in the last quarter. So this is just something very easy to answer. The SQL query is not very difficult, but still you need the agent to interact with different systems, such as your BigQuery, and maybe you want the result to store in the the result to show up in the Looker or Power BI dashboard. So this way, the agent needs to have access to these different systems. So that's one example, which I think almost all companies will need to perform data analysis more efficiently. And another example especially in the sales and outreaching, I think have been seeing a lot of success is about also making the the information enrichment of potential leads much more efficiently. So one example here is that, so there's a startup, essentially what they do is that, like an Excel UI kind of format, you can just type in the target audience industry that you are interested in, and or you maybe find someone interested in name. And once you put in that, say one column, and then the agent in the backend essentially will automatically do kind of research on that person or that company online, and then find all the most relevant information and automatically populate that sheet. Because this is something the salesperson will usually do, where you do a lot of research on that person or that company, like what's their title, and for that company, what's their recent news. And then you need to kind of manually create that information base for that user or company. But with that AI agent, you can do that very efficiently, because we'll just kind of do this web search and information gathering for you. So for the sales, especially like in the initial phase of the sales and outreaching, it's very helpful, because then, or maybe further, you can generate the email automatically. For example, if a potential lead posts something on LinkedIn and they have some big achievement, you can automatically generate an email using that agent to congratulate that person, to better form the relationship with them. So I think that's also an area where the agent could be very helpful in terms of doing the automatic web search and gathering the information. Yeah, but feel free to add in the Discord channel, like if you see any more interesting actual use cases for agents.
Sure.
Yeah. Mm-hmm. Yeah, I see Radia just joined, but I think, yeah, we just finished our presentation. So yeah, maybe that's because of the daylight saving in the US, because I'm not sure if that would affect the time in other non-US time.
Yes, it does for us. Like it's 1 hour earlier now for us.
Got it. Yeah, I hope this time still work good for you.
Yeah, it's okay.
Yep. Yeah, I think this is the end of our meeting today. Let me stop recording.